Yes, it's good.
Excellent, excellent. So if you were at the panel, this is a change of pace. This is a little more technical and taking a different angle. It's close to home and also taking a little bit of a different mindset, less critical, perhaps hopefully more constructive. Let's see. So the idea of millimeter wave, and in particular 28 gigahertz. Of course, you heard before, Andreas was very clear about the potential for industry automation. And so that's a very interesting target for millimeter wave. However, as we all know, the link budget is a great concern. So we decided to do really tier one industry hardened propagation measurements in many factories and collected over 2,000 links to understand the coverage issues as well as blockage issues. We tend to, our brains cannot stop, and we try to make models, and there was a lot of internal discussions about narrow beams in higher frequencies getting blocked by, say, industrial equipment being moved in the factory floor and causing blockage and cascading effects in higher layers, et cetera, et cetera. So we wanted to really get a handle on this. And for that, we collected over 14 million individual power measurements. We made it a narrow band so that we can do this quickly and with a lot of SNR margin. Again, I say millimeter wave, but I should really say 28 gigahertz was the focus here. So in order, sorry, too quick with my finger. So in order to understand what's going on, we separated the data into a line of sight and non-line of sight. And the executive summary, if you really need to take home points without waiting till the end, is that perhaps, so a little bit surprising, factories are much more open than you would think. Even when you have, say, car manufacturing, yes, there is a lot of metal cabinets and the like, but there is a lot of open space as well. And if you happen to be in line of sight, say in a corridor where people move or equipment carriers move, then it's very close to free space. And the antenna gains are quite effective with very little loss of gain due to beam spreading. In non-line of sight, you start seeing some 20 dB beyond free space at the 90 percentile to within 50 meters. And you do see now further gain reduction of 7 dB at the 90 percentile. We will see this is not a showstopper, and so a teaser so that you perhaps stick around to the end of the talk. But to a big surprise to us, a 2 meter square metal object could only manage a 7 dB loss. And to do that, it needed to be within 2 meters of the one of the antennas. So clearly, there is a lot of multipath propagation. We should have known that. In fact, in my previous years, as you know, multipath is one big friend of mine. And so this mindset of pencil beams getting blocked is actually not supported by data. And yes, you do block the direct path, the shortest geometric path, but there's so many other paths that in the overall power balance, you are really not affecting things very much. And we will see that having a 7 dB fade margin doesn't seem to be a showstopper. Bottom line, factories are not that big. A 50 by 50 meter factory is quite large. And you can put a single base station, say, with 4 sectors if you want, and deliver something like 130 megabits per second to 90% of the factory floor, and deliver that using something like 400 megahertz of bandwidth with a very modest 2x2 MIMO, and really implementable and inexpensive 23 dBi gain antennas at the base and 25 dBm per polarization power with a very inexpensive omni antenna terminal. So Good news. If you were in the panel, this is the opposite. Exciting news. It works. It's tremendous potential. I think a lot can be done with 130 megabits per second. If you want ultra reliable because of factory, don't be scared of the 90%. You can raise that to 5 nines if you want, especially because this is only required under sort of particular target area of well-defined high reliability coverage. So it's not throughout the factory. This 90% applies trying to cover the entire 50 by 50 meter area. So let's get a little more in detail. So most factories consist of alleys in which you have equipment in both sides or storage cabinets. And so we moved either within the same aisle or one remove, second remove, third remove, as you see in the bottom center picture. We did the measurement using a 28 gigahertz scanner with in the receiver. You see at the bottom right picture on this sort of bottom left. On the right hand side of it, you see clearly the mouth of the horn on a round table that rotates at 300 revolutions per minute, which allow us to do angular spread, power spectral versus angle. And we have a narrowband system. The left is on the bottom picture, bottom left, and the left of that picture is the transmitter. You see a smaller horn with a lesser gain. Transmitter is very simple. It's just transmitting a single CW 28 gigahertz signal. And so with that 170 dB of link budget, we can really cover all locations. So this is, as I said, industry grade. We determine the target area to be measured, and then we thoroughly scan it with all points having at least 10 dB of SNR for a measurement reliability. No points have been selectively dropped out because we could not close the budget, close the link budget, close the link, and so forth, and therefore the data is not biased by selecting only those places where it works, but it's really the target area. So we can talk about what it takes to do 90% coverage of that in a more industrial fashion, or as it has been customary in outdoor cellular. We measure 4 different factories. 2 of them were a light electronic assembly, and 2 of them were more of the car manufacturing type, automotive. And so here you see a sampling of results. On the left, you see Omni transmitter line of sight on this entire chart is line of sight. So let me bring your attention to the top right. So if you wanted to see beams, this would be the place to see beams. This is, you are in direct side transmit receive, but you're surrounded by scattering. So while you do see a strong signal coming, say, from 180 degrees, you see in the top right polar diagram of power versus angle. There is energy coming essentially in all directions from at different degrees, but clearly it has a dominant, a strong direction, which is at least tens of dB better than the other ones. But back to front attenuation is whatever the antenna provides, which is not that great as described from the beginning. So you see the different points and colors as the different factories. Nothing else. And you can see that a straight 2-point slope and intercept fit to the data gives a very good fit with only 4 dB RMS error. And so in free space, you are pretty close with 4.2 dB RMS, and you only reduce to 4.0 if you actually optimize the slope and the intercept. And so all sounds good, all sounds great. I mean, in line of sight, you are pretty close to free space, and you have very little antenna degradation. The antenna degradation statistically is shown in the bottom right, where you see the red dashed vertical line is the nominal antenna gain you would get in completely echo-free chamber, when there is absolutely no beam spreading due to angular spread. But you can see that, say, in 90% of the locations, you achieve only a gain of something in the median of something like 11 dB out of the 14.5. So we're talking order 3 dB, not a big deal. And we discuss link budget in a minute, so we'll see. what that means. So if we now move to non-line of sight, then that it becomes a little more interesting, a lot more variety. You can see the different factories pointed there, factory 1, 2, 3, 4. Yes, there is variation factory to factory, but there also the realization that really hard work by 3GPP people, and we use here the closest model. It's not the best, but it's going at least through the cloud of points. You see that free space now is very optimistic, and factory 1 in dash black is significantly worse than that either free space or 3GPP. And you see that the joint factory fit, it gives you 7 dB RMS in the big red letters and the big red dash line. So that's actually a fit going through the entire cloud, and slope and intercept continues to be a reasonable model. Dense clutter is indeed creating being spreading, but the parameters that seem to dominate behavior here are the large items, the macro items, like how high is the ceiling, how high is the clutter around you, how high are the antennas around the clutter. This after the measurements, through a lot of observation, is much more important than whether somebody blocks the quote-unquote beam. In big quotation marks, I think these beams are figment of our imagination. It's certainly not laser spots, but more like a broad illuminating lighthouses that spread over a very wide area. And when you're in non-line of sight, think of a lighthouse in fog, as you saw the other picture. So
I think there are 4 minutes left.
Okay, thank you. So antenna gain now, it's significantly degraded. So it's from a scientific point of view, this is very rewarding. It's an interesting phenomena. It's happened. There is a 7 dB reduction from nominal dash line vertical on the right. And you can see that if you want to make a link badges that operate 90% of the time, you're going to have to down rate your antenna by 7 dB. And of course, if you are aggressive and this degradation will grow as you become more directive, as the antenna gain is going to max out to something comparable to the angular spread of the channel itself. You see the radiation pattern on the left, and now it's truly coming almost from all directions. And that's another way of validating that and gain loss. So finally, the blockage, but I think I told you the punchline on this. The blockage is very exciting, a lot of fun, but it actually doesn't do a lot of blocking. So let's leave that as an interesting observation again, and a good story. We don't have to worry too much about it. So if we look at put it all together and try to see what we can do in factories, then in left is SNR as a function of distance and the various antenna combinations. But the interesting one is the plot on the right, 100 meter by 100 meter factory. That's a huge factory, by the way. And if you look at 90 percentiles, then, with Omni, it's hard. But the minute you go to 23 dB base and Omni at the UEs for cost purposes, you're in the realm of 150 megabits per second. Now, if you grow the UE gain to 10 dBi, which is not crazy, then you have multiple hundreds of megabits per second, perhaps 600-700 megabits per second, which is quite workable. And so we consider this to be a very successful or very high potential application of millimeter wave 28 gigahertz to provide in excess of 130 megabits per second over 90% of factory floor, with enough margin to cover the beam degradations and the like. So models are there, and they fit reasonably well with the RMS errors that are reasonable given the link badges we're talking about, and minimal beam gain degradation, except for the really true non-line of sight where it's significant but still not a showstopper. And good news, don't worry about blockage. So with that, I'll be happy to answer any questions.
Thank you very much, Reinaldo. And we already actually have questions, which of course you could not answer them in chat because you were talking until now. But we can take first the question of David. David, maybe you can actually pose the question live.
Okay, thank you. Thanks, Reinaldo. Very interesting presentation. I'm curious. So I'm reading my question. What is essential in the end to keep in mind if you want to build a good channel model for the industrial IoT context? Is it just a question of tuning the path loss exponent to a proper value, or is it
Yes.
or is it more complicated than that?
No, it's not. I mean, what we're finding is that if you do that, which is extremely appealing to do its simplicity, then you're going to be, very close. I remember when you actual measurements, there are clouds of points. So if you go through the cloud of points, you're already way ahead of the game. So yes, there is variability factory to factory, and I wish I had 40 factories, not 4. So yes, you point to a very interesting challenge, which is in truth in advertising, these are fits to data, and there's variability factory to factory. So the predictability it would need a larger data set, say another 4 factories that we use the same models here or the overall macro average to do predicting on a factory that we know nothing about. And if that shows still to have small errors, then as I said before, because SNR is rather plentiful, to add a 5-6 dB margin for model error seems quite reasonable. And that's what we've done in cellular historically forever. If you want to reduce that even further, then you would have to invoke some site-specific model, yet to be proven that you would actually succeed at capturing the detail required to, why at a certain distance the cloud of points has 90% plus or minus, say, 6, 8, 10 dB variability. It can be anything. I mean, the objects that are in there, et cetera, et cetera. Disposition within the columns of the building, behind the column, in front of the column, who knows? So what exactly would it take to reduce that error is a big scientific challenge, and I wonder whether it's worthwhile going after that.
So precisely, this raises the next question, which is complementary. So suppose that you have a map, a very detailed 3D map of your factory, like the shape of the inside of the building, the position of obstructing objects, and so on, which would have been obtained maybe using sensing or mobile robots. How would you be able to work out a channel model that would be based on that map? So something that would be fitted to that particular factory, but without the complexity of doing ray tracing.
Well, I would put a filtering, and I would create layers that are data-driven. What I mean by that is I would ask the question, what is essential to that feature map to achieve a prediction? And if I add detail, I am successful in reducing my prediction error, or I just satisfying my video game images of pretty pictures. So clearly the walls we could guess are important. And if you have massive cement columns supporting the roof, clearly are likely to be important. The height of the ceiling, whether there is a ceiling which is radio transparent and there is even higher open space or clutter above the ceiling. The floor is if it's just wooden floor going into a basement, or it's a cement. So I will start there, and then you stop and say, okay, now if you want to add pretty pictures, you can do that. AI, ML, automatic sensing, etc. is becoming very fashionable. But are you actually able to reduce the prediction error by inserting that into your prediction engine, whatever that may be? Grad students are very eager to start doing ray tracing and adding features, an automatic feature extraction from Google Maps, or even you can postulate a LiDAR-equipped autonomous vehicle gathering all this. But do you do any better? Because what is missing is the either artificial or human electromagnetic expertise to turn that detail in more accurate models. That's not a given.
Thank you.
Thanks, Reinaldo. We have one short question from Maxime Guyot from Huawei, and then we have to move to a general discussion with all the other speakers in this session. So, Maxime.
Okay, yeah, I'll be quick. So, hi, Reinaldo. Thank you, and I think these are very interesting results. My question is: in those measurements, you implicitly consider a point-to-point single stream link, essentially. What do you think are the possibilities for spatial multiplexing, or even possibly multi-user multiplexing in the context of 28 gigahertz communications?
Oh, yeah, absolutely. We consider this simply to be the foundation on top of which you can create all of those opportunities. As you saw, in the clutter, in non-line of sight, there is a lot of angular spread, which to me implies that you can very easily have decorrelated channels. So you could do statistical spatial multiplexing a la classical MIMO. At the base station, there is very little angular spread. So you could very easily do spatial multiplexing based on purely grid of beams. So you can imagine, and I'm jumping ahead, way ahead, but it reminds me, the benefit of being old. There was Altair, there was a product where you have something like 16 sectors at the base, but within each sector, the terminal, being a multi-antenna terminal, can support multiple parallel strings. And so you are now multiplying your spectral efficiency quite dramatically. Factor of 16 just by grid of beams. And then on top of that, 2, 3, 4 simultaneous MIMO layers.
Another good news then. Thank you.